Well, thank you. I'm glad to be here. I'm going to talk about finite field restriction estimates, and please interrupt with questions as I go. So I guess I want to motivate what I'm talking about a little bit to begin with. And so I'm going to be talking about a problem or several problems in Fourier analysis. And so let me start by trying to convince you that the problem I'm trying to solve is worth solving. And so I'll give you some background material. And so let me start with just what is Fourier analysis good for? So I guess my answer to that is I mean, obviously that's a very general question with lots of answers, but probably a good answer would be it's a way of quantifying whether or not some object is pseudo-random with respect to sort of linear objects, which is either linear equations, subspaces, subgroups, etc. And so let me give you just a very basic example of what you might say along these lines. And so if you have a set A, and so ZP is just going to be a cyclic group of order P, and you may have some sort of linear equations, and I want to ask how many solutions to the linear equation there exist in my set. So I have this set A. I want to know how many solutions to A plus B plus C is equal to X, where X is just some fixed number. Now, if A was a random set, if I just choose A to be a random set of ZP, you can just compute what this should be quite easily, and that is A cubed over P. And so, roughly speaking, you'd basically fix A and B to be anything, and then C you could just think of a random element in the set, and this is the size that you would expect the number of solutions to be. So what does this have to do with Fourier analysis? Well, so if you want to sort of quantify, so this is true for a random set, and so maybe you'd want to quantify in what makes a set look random. And so a answer to this is if the Fourier transform of the set A, so A is a set of, so I can consider it its characteristic function. I can take its Fourier transform. And if this is small, and I won't actually give a precise description here, but if this is small, then for x not 0, obviously the Fourier transform of the characteristic function of a set at 0 is just the size of the set, or the size of the set over the field size, depending on how you're normalizing your Fourier transform. But if it's small when x isn't 0, then you can actually show what you would expect in the random case to be is actually true for the set. So I guess in some sense, Fourier analysis, to some extent, is allowing us to tell us whether or not a set looks random. Okay? And so it was natural to consider various instances of sets and ask whether or not we can prove that their Fourier transforms are small, and then in some sense they're pseudo-random. So this leads to the theory of character sums, which is a very well-studied topic. And so let me just give you an example. So if we're going to work through most of this in a finite field, of order P, where P is a prime. So this is just a cyclic group of order P. And so if I just wanted to pick out a subset that has the potential to look random, I could just consider the set of powers. And so this is probably the easiest thing to do. That isn't linear in some way. Yes, and then I need some conditions to make this work. And so if I want D to divide the order of the group, or I want D to divide P minus 1, because this way this won't. If this is not true, this will just be the entire group. This will just be the entire field. And if this is true, this will be a multiplicative subgroup of the field.
So it depends on the common on the GCD of P minus 1 and D. Will not necessarily be a rate.
Yes. That's a good point. But certainly if D divides P minus 1, then this is good. And so how big is this? Well, it's going to be P to the, I guess this should be, just P minus 1. So this should be, so this should be just P minus 1 over D. So that's a typo there. And so right, and so I want this quantity right here to be rather small if I want this to be a small subset of the field. And so you could so if you just have a set of this form, you can ask for what you can ask how big his Fourier transform is, and because we've sort of linked this up with the set being pseudo-random in some sense, and then I can just you can just rewrite this in a different form. And so if I want to just take the Fourier transform of my set S of D, I can rewrite this as x in the P and let x range over all elements of the field, and then just look at basically this is just a monomial, the exponential to a monomial times some factor, and you want to know when this is small, and so this is. So you've probably, there's a well-developed theory of character sums that probably everyone has come in contact with to some extent, and so this is a very classical quantity where it's just an exponential to a polynomial, and you want to know how big this is, and so you can do more complicated things, and so I could, instead of working in FP, I could work in FP to the n, so I could work in the Cartesian n fold copies of FP. And I could similarly, I can look at some sort of Cartesian product of these or I guess this isn't a Cartesian product, but I can let x run through different powers in each of the coordinates, and this is going to carve out a subset, right? And then I could ask what the Fourier transform that is, and it turns out that after you sort of change this to sum over the entire field and normalize by the appropriate factor, this is just a polynomial character sum. And so this is an object that's quite well studied, and the reason that these objects are quite well studied is because they basically mean that sort of sets associated to them are pseudo-random, and so you want to count solutions to linear equations or related things inside that set. It gives you the ability to do that, and so there's a well-established theory of character sums. Let me just choose three well-known ones. So there's an estimate of A that dates back to the 1940s that tells me that if I have a character sum over a polynomial, then I can get a lot of so the trivial sum on something of this form, I'm summing x, I'm summing p complex numbers of modulus 1. So the trivial bound is p, and so I want to have a lot of cancellation. And so as long as the degree is somewhat small compared to the characteristic, this estimate of A tells me that I have a lot of cancellation. And so if you want to be more complicated, you want to put a rational function in here, and then you need to put some sort of non-degeneracy conditions on here, and you need to exclude zeros of this because then this blows up. So there's going to be, and some of these things I'm going to write down, I'm just trying to give you a flavor. There may be some technical conditions that I'm omitting. Then delaying is a consequence of the vague conjectures proved an exponential sum with you have a rational phase. And so these estimates do very well when the degree is small, but when the degree is big, you could ask for estimates that sort of work on different parameters. And so Bourgain has a more recent estimate where you only care about the number of monomials. Again, there needs to be some restrictions on the relationship between these exponents in the field size that I don't want to write down. But you can get cancellation if the number of monomials is small as well. And so this is all related to roughly speaking, to understanding how pseudo-random these particular sets of subsets of FP or FP to some high power are. And so this is sort of a topic that has been, there's a lot of open problems that are far from being solved, but we've also made a fair amount of progress, and this is a topic that has received a lot of attention, all around the world and in the general vicinity where we currently are. And so these character sums have lots of applications. And so I just gave you four that were the first four that came to the top of my head. You may have other ones that are favorite. So you can distribution of quadratic residues, gaps between primes. Zhang's current breakthrough used Delaney's estimate, for example. People studying the distribution or security of RSA also have used polynomial exponential sums. and for another CS applications, we're in the CS seminars, extractor constructions have been built based on exponential sums. And so this is an area where there's more to be done, but we also know a fair amount. And so what I want to talk about today is restriction estimates. And so restriction estimates are sort of trying to generalize the problem in a slightly different direction. We're not trying to just make the sort of exponential sum more complicated. But what we're trying to do is we're trying to put arbitrary coefficients on the character sum. We're trying to detect a fair amount of cancellation. And so let me set the problem up like this. So you have the set S, which is a subset of f to the n. And what I'm going to do is, before, all I was doing is I was summing the exponential over the elements of the set. Now what I'm going to do is I'm going to put coefficients. I'm going to put a different coefficient on every element of the set. And I'm going to multiply this by the exponential. Yes?
So is the field finite here? Should we think of this as
The fields will always be finite. And a lot of what I'm saying is they don't need to be prime order, but if you just assume they're prime order to make everything simpler as I go, that won't cause you any trouble. Yes.
On the previous slide,
Yes.
did all these correspond naturally to some Fourier transform?
I mean, I think it's hard to think of how Delange's does, but maybe I'm wrong. But certainly anything with a polynomial exponential sum will correspond to the Fourier transform of a set and on the other side, and the Fourier side. Right. So what I would like to do is I would like to be able to stick arbitrary coefficients on here, and still be able to say that you get a lot of cancellation. Now you run into some trouble when you try to do this, because I can just cook up these coefficients so I can just pick an A, and I can just choose these coefficients to always be the conjugate of what's over here for a particular A, and then I'm going to get no cancellation. So I can't hope to have as strong statements as I did on the previous slide, but perhaps we can recover something. And so what can we hope to say? And so roughly what we would like to say is that I can't guarantee you for every A this quantity is small, but we'd like to guarantee you in some sort of quantitative sense that for most A that this quantity is small. Yes?
So you're not composing anymore with higher degree polynomials.
Well, to some extent I am, because I'm going to let S be a subset of n-dimensional space. So in the polynomial, so when I had a polynomial, it corresponded to a set of the, I guess, the number of monomials in the polynomial. And here I'm still working in Fn. And so it's possible that this set is carved out by a polynomial, or it corresponds to a polynomial in a natural way. But at this point, I'm not requiring that. I'm just saying it's a set. I'm going to actually come up with some explicit sets in a while. But
C are general complex numbers now.
yes, general complex numbers. Right. And so I would like to say that this is small for most values of A in some quantitative sense. Now, obviously, there needs to be some sort of dependence on C, because if I make C be, billions, this is going to, really, really big. It's going to be this quantity is going to get big. But so I mean, conditioned on the coefficients being somewhat reasonable, I would like to say that this is small. And so, roughly speaking, the way that we're going to quantify that is we're going to take an LP norm of this exponential sum. And so if the sum is small, and high LP norm will be small. So the idea is, if we can control this for a high P, then this will tell us that there's a lot of cancellation.
So you have two sums who have dependency on X.
Oh, so this should be a sum over A. So I'm sorry, that's a typo. And so what I'm going to want to bound it in terms of, I'm going to want to bound it in terms of some function of the coefficients, because obviously this is, if I just multiply by a constant, the constant is going to come out. So I probably want to try to bound it in terms of something that's homogeneous in terms of the coefficients. But so roughly speaking, if we want to detect cancellation for most A's, what I'm going to want to do is I'm going to want to, roughly speaking, try to bound a quantity that looks like this in terms of some quantity of the coefficients. And so you can imagine this being quite useful in places where we're using exponential sum estimates, because I'm allowing you to stick arbitrary coefficients on there. Now, of course, I'm going to pay that I don't have I have less control over how often it's small, but I'm allowing you much more freedom in choosing the coefficients. All right, so let me reformulate the goal. So I wanted to start off by motivating this by character sums, and now I want to actually to introduce a problem which is going to be a restriction problem. And now, unfortunately, restriction theory works in a different set of notation, and so I want to sort of translate the notation into the notation that they use to be consistent with the literature in the rest of this presentation. So again, S is going to be a subset of Fn, the n copies of F, where F is some finite field. And I'm going to put a measure on S. And the measure will always be here, just the surface measure of S. So what does that mean? Well, it just means that I take it's a probability measure on S that assigns the same value to every point. So I'm just normalizing by the size of the set. And so now I'm going to consider a function that maps from the set to the complex numbers. And I can define it, and I'm going to define a LQ norm of it. I'm going to define it with respect to this measure I put up here. And so I'm just going to take the LQ norm and I'm going to normalize by the size of the set. So this is an LQ norm with respect to this measure I defined on the set. Everything is going to be discrete, so you don't need to worry about measures being complicated or anything. And so now the quantity I'm going to consider is I'm going to consider this sort of exponential sum I introduced before, but I'm going to normalize by the size of S. And I'll say a little bit why I do these normalizations in a second. And so then what I'm going to try to prove is I'm going to try to prove that this quantity right here is upper bounded, that the LP norm of this is upper bounded by the LQ norm of F. So F, remember, corresponds to the coefficients on the previous slide. And so why did I make these choices of normalizations? Well, there's a couple reasons. Most of them are to create comparisons to other problems. But most importantly, you choose these choice of normalizations because you would like to state an inequality that doesn't have a constant of the field size in here. So really what I would like to do is I would like to prove this inequality right here for all F, for some P and some Q, where the constant, which is represented by this R of Q to P, is independent of the field size. So everything's finite dimensional here, so you can always, for any P and Q, you can always put some function of the field size here. And what I aim to do is to prove estimates where there's no dependence on the field size in here. And to be able to have any hope of doing this, you need to basically normalize these things in this way. But really, these normalizations are just somewhat to make the notation look clean. And really, all we're doing is we're considering the same problem I had before. We have this exponential sum with coefficients. I'm trying to prove that a large LP norm is small, and I'm using that as a way to measure the amount of cancellation I have in the exponential sum. Yes?
What's the relationship between P and Q?
So there's no relationship yet. When I actually start trying to prove things, there will need to be certain relationships. But I'm just saying that the goal in general is to prove inequalities of this form. And so let's prove. And so this is called the restriction inequality. And so let's prove our first restriction inequality. And so if I take say the L infinity norm over here, well then it's just the largest value of this quantity right here. And so now I can just crash through the absolute values and upper bound this by the L1 norm of F. And so I always have that so I can always upper bound the L infinity norm over here with the L1 norm over here, with in fact with a constant of 1. And I used absolutely nothing about this set. This is just a very general it's just crashing through the absolute value, so it's sort of a useless estimate, but it shows that we can actually hope to prove estimates of this form. And so now, this is just what I claimed. Yes. So this is I'm defining this is a real number right here. I'm defining this real number to be the best real number such that this inequality holds. And what I would like to do is I'd like to prove that this is true where this number is independent of the field size.
And what you said is that when you write it's equal to 1, also there is an example, right? When the support of f is of size 1,
Yes.
then it's equal.
Right.
But you will not necessarily always want to find the best possible restriction constant, RQ from Q to P. You
Right.
just want to know that it exists.
Yes.
Or-
I mean, there are people who study in other settings trying to actually compute optimal constants, but here the theory is so far from understood that we're just trying to prove something.
Yeah, for those pinching qualities, right? They are somewhat related, pinching, and there they know some constants in some cases.
Yes. Right. And so this is actually a typo I forgot to fix. But so roughly speaking, what do we aim to do? And we try to prove, so this is like a trivial inequality, and we try to prove inequalities are better than trivial. And so what does that actually mean? And so you sort of have to remember sort of how LP spaces work. And so the inequality gets better as P decreases and also as Q decreases. So this is the increases is a typo. But remember so this is a LP inequality on a discrete space. Remember that these quantities get bigger as P decreases. And so if I decrease P, this number will get bigger. So it will be harder to prove with a smaller P. And here, this inequality is going to get smaller as Q gets smaller. So again, the inequality will get better as Q gets smaller. So let me actually define a particular specific problem. And so I'm going to define I'm going to actually define a subset of f of n to start actually defining a concrete problem. And so here what I'm going to do is I'm going to define the paraboloid, and the paraboloid is defined to be a bunch of so the first n minus 1 coordinates range over everything. And then the last coordinate is the dot product. So the last coordinate is just one variable, or just one number, and it's the dot product of the first vector. And so the size of this is just f to the n minus 1, because I can just choose anything for the first n minus 1 coordinates, and the last coordinate is determined. And so now I form this operator, this exponential sum associated to this paraboloid, and so if I just write out the definition of what I defined earlier, it's a quantity that looks like this. So what I do is I start with the function that's on this n minus 1 dimensional set. So when I talk about a set, the dimension of a set, I mean the exponent that is the field size to the exponent of the set. And so I define this operator associated to the n minus 1 dimensional set. And so what I'm doing is I have a function on the subset. I'm taking its Fourier inverse transform. I'm defining and I get a function on f of n now. So this is n coordinates for x. And what I would like to do is I would like to classify the set of p's and q's such that I have such that I have an inequality of this form, where this constant is bounded independent of the field size. Right, and that's just what I said. Right, so I've formulated this in one formulation, which is actually not a restriction estimate, it's called an extension estimate, because I'm starting with a function on the set, and then I'm taking its Fourier inverse, and I'm sort of taking its Fourier inverse and sort of extending it to all of f of n, and there's a logically equivalent formulation of this that's a restriction estimate that looks somewhat differently. And so the way that this works is I start with a function on on f of n. I take its Fourier transform, and I restrict it to a set, to my set P. And so this inequality right here is equivalent to this inequality up here, but notice that so this q becomes a q prime, and this p becomes a p prime, and this is just duality. This is just an application of Holder's inequality. Says that that these two statements are equivalent. right? So this is so I start with a function on the entire space. I take its Fourier transform. I restrict it to the paraboloid, and I take its LQ prime norm on the paraboloid, and I'm trying to prove an inequality that looks like this, and it turns out that this is equivalent to this up here. Okay, so I'm trying to motivate this, and so I'm trying to motivate this problem I want to solve. So I want to classify these exponents such that such an inequality holds. And so I started off by trying to tell you that this is related to understanding exponential sums with arbitrary coefficients, which would be an interesting thing to do. But there's also another reason for studying this problem, and that it is a model problem for a sort of very hard problem in Euclidean harmonic analysis that looks very, very similar once I formulate it in this way. And so let me briefly take a detour, and we'll talk about that for just a couple minutes, and then we'll come back to the finite field case. And so so in R of n, we can define a Fourier transform as well. You've probably seen that before. And so the restriction problem asks that if I give you a surface in R of n, and I have a Fourier and I take a function who's the Fourier transform of a function of n, can I make sense of that? Can I make sense of the Fourier transform for almost every point in my surface? And so I think I described this here. So a typical example would be the paraboloid. So this is a surface in say 3 dimensions. So I can put a measure on the paraboloid by taking a sort of little subset of the paraboloid and projecting it down onto the R2, which lies beneath it. And now I have Lebesgue measure down here, and so I can take the measure of this set on the paraboloid by projecting it down and using Lebesgue measure down here. And this defines a measure on the paraboloid. And then I also have a 3-dimensional sphere, and this just comes with a natural surface measure that is fine. And so what we'd like to do, so if I started with a function in L1, and I take its Fourier transform, well, the Fourier transform is continuous. And if I take a continuous function, I have no problem making sense of it at any given point because it's continuous. And so this just always, so I can always make sense of it on these surfaces. But if I take a function in L2, well, its Fourier transform can be an arbitrary function in L2. And what I could do is I can consider an arbitrary function in L2 that just blew up, that just had a singularity on the paraboloid. And then if I take the Fourier transform and try to restrict it to this, I just can't make any sense out of it because it just always is infinite on this lower dimensional surface. And so the question is, what happens when p is in between 1 and 2? And so what we would like to do is we'd like to prove an inequality that says that if we integrate, if we take the L1 norm of the Fourier transform of a function over the surface, then it can be upper bounded by the LP norm of the function itself. Now you should say, well, you're trying to figure out if you can make sense of it on the paraboloid, so how do you take the integral over it? And so what I would like to do is I would just like to assume my function is smooth, and then I can always make sense out of it. And if I can improve an inequality of this form, then for any given function in LP, I can make sense of it on the paraboloid because I can extend a linear functional. And so we'd like to prove an inequality of this form where I start with a function on all of R of n, and I take the L1 norm of the Fourier transform restricted to my surface. And so this is equivalent to the extension format where I start with a function on the paraboloid, and I need to put a measure on here, and I take the Fourier inverse transform of this, and I try to upper bound the LP norm of this by the L infinity norm of the function on the surface. Now, now you should see that we're working in the Euclidean space here, but this looks a lot like, this is essentially the exact sort of Euclidean form of the discrete problem I defined previously. And so this discrete problem I defined previously serves as a good model for this problem in Euclidean harmonic analysis. And so let me just tell you what is known. I don't want to spend a lot of time on the Euclidean case. It's a problem that's been open for roughly 50 years, and there's a lot of smart people who've done a lot of complicated work on it, and we're still far away from what is known. So ideally, what we like to do is we like to prove this with any number greater than 3 here, and it gets harder to prove as p decreases. and there's a long list of people who have decreased this decreased this number. And the star here means that this is conditional on something else. And so this is what we'd like to prove. And so we want to decrease this exponent.
On the right side, you have only infinity.
Right. So there's more refined version. I mean, so there's more refined versions where you put smaller numbers over here. But there's actually a factorization theory that says if you can put a p prime here and infinity here, then you can actually put a p prime here. So at the end point, it suffices to prove, or near the end point, it suffices to prove this within infinity. And so typically these things are complicated enough that everyone just sticks L infinity over here and tries to work with that because it gets rid of a parameter in the problem. Right.
So is it obvious we cannot go below 3?
So it's not. I mean, it's easy to prove. It shouldn't be obvious to you from what I've told you. But there is an example, and I will talk about that right now. So you can't actually prove it at 3 either, and that's because of some geometric relationships. And so we would like to prove an inequality that looks like this. And so let me remind you what this inequality sort of says. It says that if we start with a function on the sphere, so say it's supported on some little subset of the sphere right here, and I take it, and so I have this function that's supported on the sphere, and I take its inverse Fourier transform, and I ask, what is this going to look like? And the answer is it's going to be supported on a tube that is, and I'm being a little bit heuristic here, but I think that's sufficient for our purposes. And the tube is going to be oriented in the direction normal to the point. So this is, imagine this is some tiny little piece of the sphere. Well, at this point in the sphere, there's going to be a normal to the sphere. This is going to have a normal, and that this tube is going to be oriented normal to is going to be oriented in that direction. Now, how this behaves on this tube, I can't say a lot about, but I know it's going to be supported on a tube that looks like this. Now, what I could do is if I multiply this function by an exponential, it doesn't change any LP norm of this because it just has modulus 1. But what it does is it translates this tube, or it translates the Fourier inverse transform, by this number tau. So what I can do is once I sort of have a function on here and and support it on some tube, I can translate that tube anywhere around. Now I can't change its orientation in any way, but I can sort of move it around. And so if you have some function g here and it's supported on a lot of different, on say 3 different caps or a lot of different, so these are called caps, these tiny little portions of the sphere. Then its Fourier transform will be supported on a bunch of different tubes. Now the orientation, each of these, so this this cap right here will correspond to this tube right here because the normal of the sphere at this point is oriented in the direction of this tube, and but I can move these tubes wherever I want by multiplying by multiplying by an exponential, by multiplying the function on this particular sort of little cap right here by an exponential. So what could go wrong in trying to prove an inequality of this form is I could have a bunch of these tubes, they all point in different directions because these caps are all in different parts of the sphere. But I could somehow imagine that these sort of all overlap on top of each other. And if that happened, well, I'm taking an LP norm over here, and so it would be if I take a function and make it really large on a small set, this is going to get really big. And so you could imagine that if you could sort of overlap these tubes in a sort of complicated way, where they were all stacked up on top of each other, then I could actually cook up a counterexample to this inequality right here. And that's in fact what you can do. What you can do is when p is equal to 3, you can sort of arrange these tubes in a way such that they do have a fair amount of overlap. And you can disprove this inequality with a 3 right here. The question of whether or not you can sort of arrange these tubes in a sort of more complicated way that even has even more overlap is.
So for p equal to 3, the example comes just from the fact that for the Kakeya
Right. Because that corresponds to the fact that you have a bunch of tubes that point in delta separated directions that you can sort of put them on top of each other such that the area, the total area is little, it tends to 0 compared to the area of all the tubes. And so that basically leads to the existence of a Besicov set of measure 0, and that is the same example that allows you to put these tubes on top of each other and disprove this inequality with a 3 right here. And so you can actually formulate the question of just how much tubes can overlap. And so this leads to something called the Kakeya problem that I don't want to say very much about. So the Kakeya conjecture just says if I have a bunch of tubes and I take this, I don't know, L3 norm, that this quantity can't be much larger than if I just had the tubes be distinct from each other. And so I can actually sort of embed this problem inside this restriction conjecture. So I can start with this and for any sort of organization of tubes, I can cook up a function such that when I apply this restriction operator to it, I basically get that arrangement of tubes out of it. And so I can so the restriction conjecture implies that I can't overlap tubes in a sort of malicious way, and so that's something called Kakeya. And so there's a formulation of this that Noga mentioned a second ago. I'm almost done with the Euclidean stuff when we're back. You can go back to discrete stuff in a second. And so if you have a subset of R3 that contains a line in every dimension, how small can its dimension be? And so this is some question that seems more complicated because this is about sort of fractals or something, just not discrete tubes. But if I had some sort of set with a dimension was small, I could take an epsilon neighbor of it, and this is going to contain a sort of tube in a whole bunch of different directions. Because every line, there will be a line in every direction, and around each of those lines, there'll be an epsilon tube if I take an epsilon neighborhood of it. And now, if the dimension is small, this set is going to be very small as well, and so that this will imply that this arrangement of tubes that I get out of this has a lot of overlap, and so that actually implies that that would actually allow me to cook up a counterexample to the restriction conjecture as well. And so this is just to say that this restriction problem, which is a problem in Fourier analysis, that seems to be a problem in Fourier analysis in higher dimensions, is sort of intimately connected with some sort of complicated problems about how you can arrange tubes in geometric measure theory. And this is one of the reasons that we're interested in trying to solve the problem in Euclidean space. And we would like to, and so the finite field is a model case for this, where we get rid of some of the technical complications, and so it should be easier. And so it makes sense to solve it, to try to make progress on the problem in this more sort of basic setting where we get rid of some of the complications to try to build intuition for the Euclidean case.
So each result on the restriction conjecture, you mentioned all this history of the results.
Yes.
Each of them gives a lower bound for the dimension for the Kakeya?
Yes.
So like this 3.27 or something, what
So they actually use the Kakeya conjecture to prove that. But if you, but you see, so they typically the implication is if you prove restriction, you get Kakeya. But typically the history is people do a lot of work on Kakeya and they figure out complicated ways to actually turn it into results in restriction. So the implication is typically the progress goes the other way, and the machine for actually converting restriction estimates into Kakeya estimates is actually quite bad. It's only tight, like very near the endpoint. So if you have 3.3, which is the best we unconditionally know for restriction, that actually implies a pretty terrible Kakeya estimate. Right. I think, I don't think you're past. So I don't think you're past 2.5. Right, and so there's some progress on Kakeya, and so 2.5 is what Wolf had in 1995, and so this is so you're trying to get to 3, and so so the problem has been stuck for a while, and so you need to resolve this before you can actually resolve restriction, and it seems to be stuck. So this is what's going on in Euclidean Kakeya. But let me go back to finite fields. So the point of taking a detour, I know some people here are discrete, so hopefully you're not going to need to remember it to go forward, but is that we're set up this finite field restriction problem. It is interesting to us because we're trying to figure out how to detect cancellation in finite fields in exponential sums, but it's also a model problem for this really hard problem in Euclidean space that we don't know how to solve. Right. So let me actually try to say what we're trying to prove in 3 dimensions. So again, here P is this paraboloid, which is the subset of F3, and I'm trying to prove a restriction estimate that looks like this. And the restriction conjecture in this setting, the exponents, roughly speaking, correspond exactly to the Euclidean case. So I'd like to prove this with a 3 over here. And so this is the definition of the paraboloid again. And so it turns out that the arithmetic of the field actually plays a somewhat somewhat changes the problem somewhat. And so there's 2 cases. There's a case where -1 is a square in the field, and there's a case where -1 is not a square in the field. And so what we expect to be true differs depending on which case we're in. If -1 is not a square, we expect to be able to take the L3 norm and upper bound it by the L2 norm of a function. If at -1 is a square, we expect to upper bound the L3 norm by the L3 norm of the function. So we're always trying to prove an L3 norm on the left. It's just what we put on the right is somewhat different. So this is roughly what we're trying to prove in the Euclidean case, although you can't do 3. You could potentially do slightly better than 3. And the reason that I'm going to talk about in a little bit why there's a difference between these 2 cases. But let me first tell you what is known. And so there's an easy argument that I'm going to actually show you called the Stein-Tomas method that allows you to prove this with a 4 over here. So roughly speaking, for the purposes of this talk, I don't want you to spend a lot of time thinking about what's over here on the right. I just want you to think about what's over here on the left. And so the idea is that we want to put as small a number over on the left as we can. And so there's this easy argument I'm going to show you that does this when p is equal to 4. And so in 2002, Mockenhaupt and Tao were able to go below this. I'm going to give you a brief idea of how this works to get 3.6. And then there's a number of tiny improvements. So I have some sort of small, very small. I think the number I can get is 1 over 1035 beneath what Mockenhaupt and Tao did. And if you assume a whole bunch of instance geometry that we don't know how to prove, I can get down to 3.5. And so I'm going to talk a little bit about the ideas that go into these proofs in a second. And so when -1 is a square, the problem is considerably harder. And so you have the Stein-Tomas again at p equals 4. And then I have an argument that recovers what you get over here in the case that -1 is not a square. But there's a number of additional complications that enter in this case that are that will be very interesting for things I'm going to talk about later. So let me actually show you how to prove a restriction estimate. I guess I should prove something here. So I'm going to use the Stein-Tomas method, and I'm going to want to prove a restriction estimate. And so I'm going to prove this with an L4 on the left and an L2 on the right. And so it turns out if you remember, I said that the problem was that the inequality is equivalent to a different inequality. And the inequality that's equivalent to is this inequality right here. These 2 things are logically equivalent. So I start with this function g on F3. And then I take its Fourier transform, and I take the L2 norm restricted to this paraboloid. And I want to prove this inequality right here. These 2 things are equivalent. So what I have is the first thing I know is that I can upper bound the L2 norm of the paraboloid by f squared times the L2 norm of f on F3. And how do I do that? Well, I just expand everything out, and I say use Parseval. I guess you prove Parseval by expanding everything out. If you just expand out the definition here, you can get this estimate. And so this is an L2 to L2 restriction estimate, but it has dependence on the field size, so it's not particularly good. So that's one thing you can do. And there's a more subtle thing you can do, and which is if you take the L2 norm and you expand it out as a inner product, and then what I can do is is I can use Parseval to write as an inner product. So I can write, so if I take the inner product, so I have the inner product of g hat with g hat, and if I take Fourier transforms, I can write this as the inner product of g with the convolution of the Fourier transform of the characteristic function of the set, and then I get this right here. This is just Parseval. And so what I can do is I can upper bound this by the L1 norm of, so I'm going to actually do this in detail in a second, but roughly the idea is if I can prove that the Fourier transform of the measure of the paraboloid is small, then this also gives me an estimate on the L2 norm of f hat restricted to the paraboloid. And the idea is that this is just enough, and so this is what I will eventually prove. I'll do this on the next slide. But if I prove that if I have the fact that the Fourier transform of the characteristic function of the paraboloid is small, then this is a good estimate. Then if I just combine these two, then I actually just get this up here. So really the only thing that the Stein-Tomas method uses is that the Fourier transform of the surface that I'm working on is small. Right. And so let me actually do some computations. So I want to compute the Fourier transform of the surface measure of the paraboloid. And so the surface measure of the Fourier transform of the surface measure of the paraboloid is just this expression I've written down here. So I guess sum over the exponential over the paraboloid. And so at 0, this is just the sum. This is always 1, and this is just the sum over the paraboloid. And so the Fourier transform is 1 because I've normalized by the measure of the paraboloid here. And so then let me do a computation now when x3 is not 0. And then what I can do is I can sort of rearrange this sum. And all I've done is I've factored out the one coordinate here and one coordinate here. If you just use the homomorphism property of an exponential and expand this out, you'll get this up here. And now what I'm going to do is, so this is just rewritten. And I've just basically completed a square. And so this quantity is just equal to this quantity. If you expand out this square right here and you add this back in, you'll just get this quantity up here. But now what I can do is this sum right here. So this part doesn't depend on xi of 1, and this right here is just summing. So I sum xi of 1 plus some quantity over all of xi of 1. So this is just summing over all the squares. And so so I'm just going to call this function that sums over all the squares. This is a Gauss sum. I guess this should be an x of n. That's another typo. But if I just use the definition of this and plug it into here, I get that the Fourier transform is equal to this. Now, you may remember from elementary number theory, it's not actually very hard to prove, although I'm not going to prove it for you, that there's a fair amount of cancellation in a Gauss sum. So I'm summing p complex numbers of absolute value 1, and if you just take the L2 norm, if you just square this and sum it, you'll see that the value of this when x is not 0 is just the square root of p. So there's a fair amount of cancellation here. And so if you just actually insert this into here, what I get is this is going to be the size of the square root of p, and so then when I square that, it's going to be p. So this is just going to be let me go back here. So this is going to be 1 over p, right? Because I get a p from this term right here, and this is a p squared in the denominator. Okay. And so now what I want to do is I want to actually prove my restriction estimate. And so what I'm going to do is I'm going to take an arbitrary function g that lives on f3, and I'm going to do what's called dyadic pigeonholing. So I'm going to take my function and I'm going to restrict it to level sets. So E of I is going to be the set where g is equal to 2 to the minus I. And so I can always normalize things so the L2 norm is 1. So the L2 norm, the P norm of g is 1. So that means that I can assume that the largest value the function takes is 1. It would just because the problem is homogeneous, so I can do this. And then what I'm going to do here is I'm going to let E of I be just it's a level set of the function, just everywhere the function is equal to 2 to the minus I, and I really only need to consider logarithmically many of these, because once you go up logarithmically many i's, then the function is very, very, very small, and you can handle it very trivially. Right. So this is a level set of the function, and so now I have this inequality from Parseval that I told you about. This is just from expanding out the L2 norm. And so I'm just going to assume that the function. So what I'm going to do is I'm just going to take G and I'm going to break it apart with the triangle inequality and consider each of these level sets separately. And so roughly speaking, I can just assume that my function now is the characteristic function of a set. And so now if I just, I had this L2 estimate I just got from expanding things out, and if I just plug in E, and I assume that the size of E is f to the gamma, then I can upper bound this by f to the, so I can just, if I just actually write what this is, well, if this is a set of size E, this is going to be f to the gamma over 2, and I can write it, I can just rewrite this like this. And now if gamma is bigger than 2, I can upper bound 1 plus gamma over 2 by 3 gamma over 4. This is just elementary fact about real numbers. And so, but this is equal to the L to the 4/3 norm of E, right? Because E is a set of size f to the gamma, and so if you take the 4/3 norms of that, you'll get f is greater than 2. Is yes, right. So what have I shown? I'm trying to prove that the L2 norm of an arbitrary function is upper bounded by the L4 that this norm right here is upper bounded by the L4/3 norm of an arbitrary function. And I can do this as long as the set is greater than the size of the set is greater than gamma to the 2 squared. And so now I need to just consider sets the size where gamma is less than 2. And so here what we're going to do is we're going to use this decay property that we previously proved. So E is now going to be a set of f to the gamma where gamma is less than 2. And now what I can do is I can expand out the L2 norm like this. And so this is where I was saying previously. What I do is I use Parseval, so I can write the L2 norm as the inner product of the function with itself, I guess to the 1/2. And then what I can do is I can take Fourier transforms, and I can get the original set itself. But then I can write. But then I had, since this is a restriction to the paraboloid, I can stick on the characteristic function of the paraboloid, and then when I take the Fourier transform, I'll get the set convolved, because if I take the Fourier transform of the product of two things, it becomes a convolution. I get the convolution of the characteristic function with the Fourier transform of the characteristic function of the paraboloid. Okay. Now what I can do is remember that the characteristic function of the Fourier transform of the characteristic function of the paraboloid is equal to the Dirac delta function, because it's 1 at 0. But when x is not 0, then I actually have some decay here. I know that it's upper bounded pointwise by 1 over the field size. And so now what I can do is I can just plug this in for the convolution here. And so I'm going to have so there's going to be one term which is going to be E convolved with itself, which is just the characteristic function of E convolved with itself, which is just itself. And so this is going to give me, when I do this, I'm just going to have the inner product of the characteristic function of the set with itself to the 1/2. So this is just going to, so the contribution from the delta term is just going to be E to the 1/2. And then I'm going to have another term which is going to be from the convolution with this part that's small. And so what I can upper bound this by is, so let me just pointwise consider what's going on in this part right here. So the characteristic function of the set convolved with this function k is, if I just write out what the definition means, is just this expression right here. And I know pointwise that this k is rather small, and so if I just replace this by the absolute value, I'm going to get 1 over f, and then if I just sum E over all the points, I'm just going to get the size of E. And so now if I plug this into here, I'm just taking the inner product of this function with this quantity right here. And I can upper bound that by e times f to the minus 1/2. So I get one. So I get an e from this right here, and I get an e from this right here, and then take the square root, which gives me this e, and then I have this f to the minus 1/2. But then it gets hit by this 1/2, and it becomes f to the minus 1/2. And so I've proven this. I've proven this right here. This inequality. Now, I claim that if gamma is less than 2, I can upper bound this by this expression right here. And so again, this is just elementary algebra. And so this, both of these are upper bounded by f to the 3 to the gamma to the times 3/4. And so this is equal to the L4 thirds norm of the characteristic function. So what we've proven is we've proven for any characteristic function, I can upper bound the L2 norm of the Fourier transform on this set by the L4 thirds norms of the characteristic function itself. And then I can just use this duality to rewrite this in a different way. I can rewrite this as and so I've only proven this for characteristic functions because the proof goes a lot cleaner this way. But you can actually chop your function into 2 pieces and apply one part of the argument on one and another part of the argument on the other, and you can actually recover this for all functions. And so this is equivalent to the L4 norm of the Fourier the extension of f being upper bounded by the L2 norm of f. And so this is the Stein-Tomas theorem in this setting. And so the goal, so this is typically, we don't use a whole lot. All we need is some decay in the Fourier transform of the set we're working with, and we can do this. And this tool is used all across Fourier analysis in discrete as well as Euclidean settings. This Stein-Tomas argument, because you don't need a whole lot. All you need is a little bit of decay to make it work. And so what we'd like to do is we'd like to go past it.
So the levels here where in order to pass to something that looks like a characteristic function?
Yes.
Right. And you don't even use this operating term, or you don't care?
Right. So technically speaking, I prove this with a logarithm here. But what I'm saying is that if you actually were willing to be more dirty in the details, you could have actually just split the function into 2 pieces and used one of the arguments on one piece and used the other argument on the other piece. So Mockenhaupt and Tao figured out how to go beyond this. In the case of -1 is a square. And so let me sort of explain. And so I'm not going to be I'm not going to go through the details so carefully here. I'm just going to try to give you an idea of how their argument works. And so you want to prove an inequality that looks like this, where p is below 4, because at 4, this is what the Stein-Tomas argument gives you, and you want to go below it. And so you can write this in the dual formulation. I've been going back and forth between the 2 formulations all through the talk, and I'll continue to because it's convenient. And so what you would like to do is you'd like to prove this, where this exponent over here is bigger than 4/3. So again, if you're willing to lose logarithmic factors, which you can typically get rid of, but I'm going to be willing to do through this entire talk to make things easier, I can always assume that my function is a characteristic function. And so, so it's a function on F3, and I'm going to call it E, and this is just these dots are just going to be the elements of the set of the function, the set, which is the function is a characteristic function of the set. And so what I'm going to do is I'm going to slice it vertically. I'm going to try to understand the slices. And so there's a variable that parameterizes the height here, which is the last coordinate, and I'm just going to take a slice of it at some place, and I'm going to consider what happens. And so what I'm going to do is I'm trying to prove this an inequality right here, where these are, so E sub s is just going to be the restriction of E to a particular slice. And so as I range over, I can just parameterize my function as a sum of the different slices. And I'm just going to write the L2 norm like this, which is what I'm trying to bound. I'm just going to use a triangle inequality to pull this out, to pull the sum of the slices out. And I'm just going to try to understand what happens on a single slice. And so I've just written this function. I just consider the function as a sum of slices, and right. And I'm trying to estimate this, which is what I was saying before. And so what I'm going to do is I'm going to use. I'm going to be a little bit vague on actually how you do this, but you're going to use Holder's inequality at some point in some clever way to upper bound the L2 norm in terms of an L4 norm. And then once you're working with an L4 norm, you can expand it out. That's the nice thing about even integers is you can expand them. You can expand out the norms, and it turns out it turns out that you sort of expand this quantity out and try to understand what it looks like. The size of this quantity will be upper bounded by some other problem, which I'm going to describe for you here. And so I'm going to start with this function. So I'm going to I have this at E of s. And it's a slice of this three-dimensional of a set in 3 dimensions, which means it's a function in 2 dimensions. And so these green dots represent the points in the set. So I have this 2-dimensional set, and the green dots represent the points in the set. And then I also, in some way that I'm not going to describe, I can associate a set of lines to the point in the set as well. And so so these are drawn in blue here. And if you want to understand this L4 norm after some sort of easy manipulations, what it does is it actually boils down to counting the number of incidences between these lines and these points.
The lines came from where?
Come from the set as well. So I think one point is the intercept and the other point is the direction. Or it's some natural way. And so you have n points and n lines. And you want to count the number of incidences. And so there's an easy bound that you can apply, and this is, I think people call it the Cauchy-Schwarz bound. And it tells you that you can have at most n to the 3/2 incidences. So Mockenhaupt and Tao use this, and once you sort of add up all the contributions over all these slices, you can actually get, and I wrote something in the wrong place. It should be the p here should be 18/5, and this should be a 3. But roughly, so what they do is they upper bound the L to the 18/5 norm of this function in terms of the L2 norm. So 18/5, if you get your calculator out, is equal to 3.6, which is below 4. And that our goal was to prove an estimate below 4. And so if you actually go through this argument of slicing and estimating the L4 norms of these slices, you can actually get it down to 3.6.
This is just from the trivial estimate for it.
Yes. Right. And so
If you break it into slices and use some constant there, you don't actually lose much.
Right. I mean, you lose some. You actually, I mean, roughly speaking, the estimate you're proving on the L form is sharp. So in some sense, you can only, and this is probably true with the 3. So you probably are losing a fair amount.
So that's probably due to the loss there.
Yes. So yeah, so the fact that this isn't sharp is definitely coming from the fact that we took the slices, but we don't really have a much better way of doing this. And so there's so I think as Noga was sort of inferring, is there's actually an improvement to this incidence problem. Now you need some conditions on the points and lines. I'm actually going to talk about this in a second. And the idea is to try to employ this in the argument. And this is what I do. It wasn't exactly easy because I wasn't the first to have this idea. But and so let me briefly talk about some product estimates. So if you have a subset of the reals, and you want to know how big a sum set could be, so this is the set of all possible pairs of sums. It can be as small as the size of the set. Well, maybe 2 times the size of the set. I'm not being so precise with constants here. And it can be as large as a squared, so I guess all the sums are distinct up to sort of reordering. And then I could also consider the product set. And so I had and it could be roughly the size of the set, or it could be as big as the square of the size of the set.
By the way, if you want to make a break at some point for 10 minutes or something, it's up to you.
Okay. Oh, I didn't know that. Do you guys feel like a break? What's common? Do we take a break? Okay, so let's take a 10-minute break. Yes. Great.
delta.
Yes.
Right. And you said at the beginning, somehow this approach, you cannot get below 3.5 no matter what, or
Right.
or it's,
Well, if you assume your instance estimate right, well, I'll continue. Okay, so we'll take a brief tour into some product estimates. Maybe I'll skip a little bit coming up soon. But so if we're in this subset, we have a subset of the reals. The sum set can be between the size of a and a squared, and the product set can be between the size of a and a squared. And so this happens if you're in arithmetic progression, and this happens over here. So the sum set is as small as possible when you're in arithmetic progression. The product set is as small as possible in your geometric progression. And the question is, can this happen simultaneously? And so Irish and Zamretti have a conjecture about this, and they claim that, that one of these will always be at least nearly as big as possible, either the sum set or the product set. And so there's some. So Irish and Zamretti, I guess in '83, I guess that says, got some. So the trivial lower bound is a. And so you want to get some sort of power improvement. They did a to the 1 plus delta. And so there's been a long line of improvements. At least when I wrote these slides, the record was 4/3, but due to Salamoji.
Should they be minus?
I'm sorry?
Should they?
Yeah, it should be minus. Well, I was trying to, I think I was, yes. I think I was subsuming that in the notation. Right, and so the question naturally comes up whether or not you can do the same thing in a finite field, and so you need to be a little bit more sort of careful, because if A is the entire field, or more non-trivially a subfield, then these things will always be equal, because the sums inside a subfield are closed, and products in a subfield are closed. So I can't hope to prove this. But there's a nice result of Bourgain-Cass and Tao that has led to a lot of interesting things in other areas, that says that as long as A is not near a subfield, then you can actually get some product improvement. And so this is actually equivalent, at least qualitatively, maybe not quantitatively, to the question of getting an improvement in this Zamre-Trotter incidence problem. So you have n lines and n points, and you want to know how many instances there are. And so this Cauchy-Schwarz boundary used earlier is n to the 3/2, and you can get a slight improvement on this from a sum product estimate. And it turns out that if you actually if you can improve this with a slight improvement, then you can actually get an improvement on sum product. So at least they're equivalent.
Can you say a bit more the intuition for why the sum product estimate tells you something about this incidence?
So it's a bunch of applications of Wallag-Zamretti Gowers. I don't think I have a good.
But it's not like an obvious thing.
It's not obvious.
Okay.
There is an easy argument of Alcaresh, which I couldn't reproduce on the spot, of if you have an instance estimate of how you get a sum product estimate. But that's an easier direction.
For the reals, it was pretty simple. So that's this allocation.
Yes. But I think that works over any field.
So you were saying, right, so from the incidences to the sum product, it's easy.
Yes.
Right, but other direction, you need some more.
Yes. And in fact, the machine is quite terrible, because we have I don't know. I mean, so you need to put parameters to quantify how far you are from a subfield. But in the sum product world, we have things like 1/10 over here in the finite field case, and the exponent over here is like 1/600, because the machine for going between them is not so good. Right. And so then if you just sort of insert this into the Mockenhaupt-Tao argument, it's not, as my own work, so I don't want to say it's completely trivial, but it's if you sort of insert it and you need to adjust some of the things, you can get a small improvement on their exponent. And if you assume everything that possibly could be true about incidence geometry, you actually get down to 3.5. So Mockenhaupt now got 3.6. Using this incidence theory, you can get to 3.6 minus delta. But if you assumed basically much more about incidence geometry than we can prove but could possibly be true, you get down to 3.5. So we're still quite a far a ways from 3, which is the conjecture. And so I wanted to say something about what happens when -1 is not a square. And so here the restriction problem it becomes somewhat different. And so this is because, so this is the definition of a three-dimensional paraboloid right here. And so I can reparameterize it if negative 1 is a square in the following way. I can rewrite the elements like this. And then so the third coordinate is equal to x squared minus I y squared. And then I can take this I out and make this x squared plus y squared. And so if you sort of play around the algebra, you'll see that this becomes, this is equivalent to a hyperbolic paraboloid. So this is, so here what I'm doing is I'm taking two coordinates, I'm taking the dot product in the third coordinate. And here what I'm doing is I'm taking two coordinates, I'm taking just the product in the third coordinate. And so if negative 1 is a square, I can do this reparameterization in these two. These are two different parameterizations for the same surface. So what you'll notice here is that this contains lines now, because if I fix omega 1 to be some number, then I have omega 2 times whatever that number is times omega 2, and so this is a line. So this is actually what's called a hyperbolic paraboloid, and so it's a it contains is a parameterized family of lines. It's a parameterized family of lines in two different ways. So if you fix this coordinate, I get a line, and the rest of this. And if I fix this coordinate, I get a line, and the rest of it.
So you're explaining why it's more difficult.
Yes.
Because there are lines which are many incidents.
So the issue is that I'm going to get to that in a second. So it's just the nature of the surface itself is just different because it contains lines. Is the only point I'm trying to make at this point. Right. And so if you take a line, so if I just take the characteristic function of a line and plug it into this extension operator, then I'm just actually going to get out the characteristic function of a plane. And if I can just test the inequality I'm trying to prove on here, I guess I don't want to go through the calculations in detail, but if you just test it, you'll see that you need to make this the right-hand exponent at least 3 to have a hope of proving anything. And it's because just by testing on this characteristic function of a line. So let me ask what goes wrong when we try to run the Mockenhaupt Tao argument in this case. And so I guess what I should say is that if you actually test the characteristic function of a plane in this, so this is the dual inequality. So I'm starting with the function on F3, and I'm taking the Fourier transform and restricting it to the paraboloid. If I plug in the characteristic function of a plane at the 4/3 exponent, which is the Stein-Tomas exponent, which is the thing we proved using not much at all, then it turns out that this is an L2 over here. This L2 is sharp, in the sense that you cannot hope to prove anything. You can't hope to increase this exponent with while having a 2 over here, while having a 2 in this exponent. And so the Mockenhaupt Tao argument exploits very. I mean, the first step of it is to take this L2 norm and to expand it out. And so if you want to increase this exponent over here, which corresponds to going below 4 in the dual formulation, then I need to change this 2 to a smaller number. But once I change 2 to a smaller number, I can no longer use Parseval and Plancherel and all these L2 tricks, and so the problem becomes much more difficult. Right, and so we need to decrease this exponent to have any hope of increasing this exponent over here. And so this is just where I said Mockenhaupt and Tao sort of uses this in a crucial way. And so the bad example to keep in mind is when f is the characteristic function of a plane, because this is what shows that you can't you need to increase the 2 if you need to decrease the 2 if you increase this. And so this is a good example just to keep in mind as we go further. The characteristic function of this plane is the problematic example. So let's just actually try to run the argument anyways. I mean, we know it's not going to work because we know that the exponents don't work out, right? But we can still try to run it and see what we get. And so I'm going to take my set E, and I'm going to slice it again. And I'm going to just pull these slices apart with the triangle inequality. I'm still keeping a 2 here because the argument only works with the 2. And so we know we can't win, but we're just going to do it anyways. So what you can do is, if these points when you slice this, if the points lie in a line, then everything you're doing so you can take this L2 and you expand out in L4, and you basically you don't get this incidence problem anymore because everything just degenerates. But if you take this slice and it doesn't concentrate on a line, then what you can do is you can actually expand out this L4 norm and get something useful because the problem to some extent doesn't degenerate. So it turns out that if you had this set and every time you sliced it, the set didn't concentrate on a line, well then you could still run the Mockenhaupt Tao argument. And so the problematic case is when every time you slice it, you get something that looks like a line. And this is in sync with our intuition, because the problematic case is when all the points are on a plane, and if you slice a plane, you get a line. So this is exactly the problematic case. And so let me also say, if you remember when we ran through the Stein-Tomas argument, the argument there was a distinction that happened when the size of the set was equal to the size of the field size squared. And that's when we split between one case and the other case. And it turns out that either of those arguments actually give you something slightly better if you're bigger than 2 or less than 2. So really the problematic case is only when E is roughly the square of the field size. And again, this should jive with our intuition because the plane in F3 has f squared. And so this is consistent with this problematic case. And so now what I do, and so I'm describing this way that I go beyond Stein-Tomas in this case where -1 is a square, is so I'm going to split into several cases. And now I'm going to assume this problematic case that we sort of know about, I mean there may be others, but the one we know about, is when all the points lie on a plane. Now if it actually is the characteristic function of a plane, I can explicitly compute things, but it may just be 1 millionth of the points on a plane in some strange way, and I don't know what the Fourier transform of that looks like very well. But what I do know is if I have a function that's supported on a plane and I take its Fourier transform, well, it's going to be constant in directions normal to the plane. Right? So the Fourier transform this is a set, and I take its Fourier transform. And I don't know what the Fourier transform looks like, but I know it's constant along lines normal to the plane. And so what I can do is that if I actually am in this situation, I can what I'm trying to control here is I'm trying to control the L3/2 norm of this Fourier transform restricted to the paraboloid, and I can actually understand how these lines intersect the paraboloid. Now, it turns out that's the case that the paraboloid contains lines, and one of these lines may actually be inside the paraboloid, but only one of the lines can be inside the paraboloid, and all the other lines can only hit the paraboloid in one place. So this actually is a characteristic function of a plane. What you're going to do is you're just going to get one line, and it's just going to be inside the paraboloid, and this is going to cause the problem. Now, if it's sort of a more complicated function, I can sort of geometrically understand how these lines intersect the paraboloid. I can actually prove if my function lies inside a plane. If I have any function lying inside a plane, I can actually prove the full conjecture for that function. Now, you can actually sort of degrade this a little bit and say that even if your function is contained in a small number of planes, then since we can prove the full conjecture for one plane, if you're just contained in a small number of planes, I can prove a weaker estimate. I can prove something that's better than Stein-Tomas, but weaker than the full conjecture if you're contained in, say, f to the delta planes. And as delta increases, the estimate gets worse. And so let me say here, I said in the beginning that I can't use L2 methods, and I used L2 methods in one part of it. And here's the place where I'm not using L2 methods, because I'm actually just geometrically understanding how the Fourier transform intersects with the paraboloid, and I don't need an L2 to make this work. So this is the stage where I'm not using L2 methods. And so by being more careful, as I said, I can handle the case when when the set is contained in a small number of planes. And so the last case, so this boils down to one case which we can't handle. And that's where I have the set. The size of it is f squared. Every time I slice it, I get a line. And it's not contained but the set is not contained in a small number of planes. And so it looks something like this, because I can't draw a bunch of planes that contain all these lines, but every time I slice it in a vertical direction, I get a line.
And every time means many times, or approximately.
Right. So you need like this to be very robust in a whole bunch of parameters, but I'm just going through the structure of the argument. Right. So you need these statements to be very, very robust. And so what I can do is I go back to the L2 methods, because I got rid of this one case I couldn't deal with, this planar case where the L2 methods failed, and I go back to the L2 methods, and what I do is I can rewrite the L2 norm of the Fourier transform is the function, the inner product of the function with the function convolved with the Fourier transform of the surface, and then I can use Kakeya's inequality, and I can upper bound this with this, and so then what I want to do is I want to understand this operator right here, which starts with a function and convolves it with the Fourier transform of the surface. And so I want to understand this operator, and so I can tell you what it does geometrically. So you need to actually go into the definition of it to figure this out. But if I have a function that's supported on a line, and the line is sort of in a direction like this, so it's a vertical, it's on one vertical slice, and it's pointed in a direction oriented to the axis, and I apply this convolution operator to it, what happens? And what I get out is I couldn't draw this, so I need to describe it to you. Is I get it becomes a set of planes through this point. So this is supported. So if you look at this on the face, this is supported on a single point, because it's a line going into the cube. And over here, and so it's some function supported on this line, and I apply this operator to it. And what I'm going to do is I can get a whole bunch of planes through this line. And what governs what these planes are? Well, it turns out that f of s has a one-dimensional Fourier transform, and each of these planes is going to correspond to one of the Fourier coefficients of f of s. Right. So these correspond to the Fourier coefficients of f of s. Now it turns out that the only time so when I apply this operator to f, where f is this sort of union of lines, I'm going to get some big mess that looks like this. Because I'm going to get a plane through every point that corresponds to. So on every vertical slice, I have a line, which is just a point on this face. And if you just look at this face on, I would get a plane. I would get a set of planes through each of these points. And it turns out that the only way this estimate is not sufficient to go beyond Stein-Tomas is if all these planes stack up on top of each other. Now, if you think about it, all these points. So I have all these. So I have this point, and I get all these sort of. So if I just think of it as a two-dimensional problem, I have this point, I get all these lines that stick out of here, and I get this point, I have all these lines that stick out of here. And the only way that I have a problem is if all these sort of lines coincide with each other. Now I claim that I've actually ruled out that case, because the only way these lines can only stack up if these points are all on the same line. And if these points are all on the same line, then I'm actually in the previous case of a lot of these lines lying on a single plane. And so I've sort of put myself in a case where I know that doesn't happen, and so I know that these lines can't stack up too much, and so I can get an improvement in this case as well. And so that actually covers all the cases. So we had the first case in which the size of the set was not close to f squared, and I can just get better. I can just do better by the Stein-Tomas argument itself. And then I have this case where most of the vertical slices don't concentrate on a line, and then I can run the Mockenhaupt Tao argument. And then I have this case where E is contained in a small number of planes, and then I can just do a direct computation where I can understand how the Fourier transform intersects the paraboloid. Then I have this fourth case where slices of E are contained in line. So every time you slice in a vertical direction, you get a line, but these lines don't concentrate on a small number of planes. And in that case, I can actually understand this convolution operator that I've associated to the problem.
This goes all the way down to 3.6.
It does. And so
This Stein-Tomas does better. So if E is not F squared, but it's close to F squared.
right. So if for instance, I think if you're below 1, I mean, 1 I don't think is the right number, but if you're below 1 after the 1, then I think Stein-Tomas implies the whole thing. I mean,
But if you're close to F squared.
I mean, it gets worse as you get closer to 2. But I mean, once you move any way away from 2, you do better.
Yeah, but you want to go down to 3.6, so you have to go.
You do have to go quite a ways away. Yes.
So I'm kind of don't quite understand how come these 4 cases cover everything and enable you to go down to 3.6 or even 3.6 minus delta in each case. So suppose, for example, we are in case 1, but E is really F to the 1.999.
Right. So you need to make these quantitative. I mean, so I didn't want to put too many parameters on here. So I think, I mean, this is off the top of my head, so I may be wrong. But I think, you know, I think you can have, like, if F is bigger than, like, 9/4, then you get 3.6, just from Stein-Tomas. And if it's lower than, I don't know, some number less than 2. So you actually, you need to partition into cases and say, okay. And so these arguments, I mean, I sort of described them sort of crudely, but you can actually run all these sort of geometric arguments I came up with quite efficiently. And it turns out the bottleneck is still so one of these has to be the bottleneck where you can't go further, and it's actually still the Mockenhaupt Tao argument. And so it seems like you can actually run actually all these things, I believe, down to 3.5. So it seems like down to 3.5, the Mockenhaupt Tao is your only problem. And since it's still the problem, you can actually you can combine it with the sum product method and do slightly better. So you can go slightly below 3.6.
Now, is the reason that that's the bottleneck mostly because of this loss in doing the slices at all? Or what's really causing the loss of these things?
Is the slices?
Is the slices?
Yes. It seems rather inefficient to slice it, but we don't have any. And you see the last method, I mean, in some cases you need to exploit cancellation that you're throwing away when you do the slices. And I had to deal with that in the previous case, but it was in the, so I didn't slice in this very last step. I actually just understood how the operator worked, and I didn't slice. And I had to do that because you need to exploit cancellation that you throw away in the slices. You can prove that you can't go below it with just slicing. Right. And so I just want to briefly talk about one other thing, and then we'll be done. And so I want to talk about I talked about Kakeya estimates in Euclidean space, and I want to talk about briefly in finite fields because here the state of the art is better. And so I guess I want to say in the restriction problem, 3.6 is basically what we can do in 3 dimensions in the finite field case, and 3.3 is what we can do in Euclidean in the case. So the Euclidean theory seems to be much ahead of the finite field case. But the finite field on the Kakeya problem is reversed. And so E is considered a Kakeya set if it contains a line in every direction. So you can make sense of this in the finite field. Right, so there's definition of a line. And so we say E has dimension alpha if I can prove a lower bound of f to the alpha on the size of the set. And so Wolf, I think around in the mid-90s, conjectured that a 3-dimensional Kakeya set has dimension 3. And so how big must one be? And so there was a series of improvements on this. So Wolf proved 2.5 in the mid-90s. He proved the same thing in the Euclidean case. And then Bourgain, Cass, and Tao, 3 rather sharp guys, got some tiny improvement. And this is actually where they introduced the sum product estimate. This is one of their motivations for proving the sum product estimate in the first place. And so they were motivated by sort of similar considerations when they proved the sum product estimate. And then Dvir in 2008 just proved the full thing, or came up with a method that proved the full thing with that this is equal to 3 in a very much simpler way than the previous methods. So far, this hasn't translated to the Euclidean case. So for a long time, it was thought that the Kakeya problem in finite fields was not super relevant to harmonic analysis because it didn't seem to have an analog with the restriction problem. So if you remember, if you go back to the Euclidean case, what I did is I had a function on the paraboloid, and and I took its Fourier transform, I was concentrated on this tube. But you sort of can't do this in finite fields. If you sort of take a small little part of your finite field and take a Fourier transform of it, of the paraboloid on that, it doesn't concentrate on a tube. It just sort of spreads out all over space. So you sort of couldn't mimic this example. And so so Mockenhaupt and Tao looked at this, and they thought that the problems weren't connected. That so in Euclidean space, the finite field, the restriction problem implies Kakeya, and this wasn't true in finite fields. And so it was thought to be less connected. And so it turns out that they are connected. And so this is a new result. And so the restriction conjecture for hyperbolic paraboloids in 2n-1 dimensions implies the n-dimensional Kakeya problem. And so this is new. And so so this is the hyperbolic paraboloid again in n dimensions. And so this is actually in 2n+1 dimensions, because each of these coordinates is n-dimensional, and then I add this extra coordinate on the end here. And so let me remind you that in odd dimensions, when -1 is a square, then this is equivalent to the standard paraboloid. So I'm actually making a statement that this is actually true for the standard paraboloid in the case where -1 is a square. And so let me explain why that's the case. It's actually quite easy to see once you think about it correctly. And so consider this is the hyperbolic paraboloid in 5 dimensions. So this is a 2-dimensional coordinate, this is a 2-dimensional coordinate, and this is a 1-dimensional coordinate, which is the dot product. And so now we can consider a subset of it, which is I'm going to take theta, which is just going to be a fixed 2-dimensional number or element in my field, and I'm going to consider, and so this is a plane inside the paraboloid. So if you remember, the 3-dimensional paraboloid has lines in it, the 5-dimensional paraboloid has planes in it. And so now I'm going to take the Fourier inverse transform of the characteristic function of this. And now this is a 5-dimensional function. I can't draw 5-dimensional functions very well, but I'm only going to draw the last 3 coordinates. And so if you think about so this is a 2-dimensional plane, a 2-dimensional plane in 5 dimensions. And so this Fourier transform will be a 3-dimensional affine subspace. And in the last 3 coordinates, I'm only going to get a line. Because it's a 3-dimensional object in 5-dimensional space, but it turns out that in the last 3 coordinates, I always have the first 2 coordinates, and in the last 3 coordinates, I only have a line. And so this is going to be in the direction of theta, where theta corresponds to the theta I shows up here. And so I can translate this wherever I want by just multiplying by an exponential. So this is the characteristic function of the set, and I can just translate it wherever I want by this. And so now if I had a 3-dimensional Kakeya set, what I could do is I can just take, every line will correspond to a different plane inside the paraboloid, and I can just cook up this function right here, who will be supported on this Kakeya set. And since the support of the Kakeya set is small, these tubes need to pile up quite a bit, and this will actually disprove my LP inequality for the that is the finite field restriction problem. And so that it actually turns out that the 3-dimensional Kakeya conjecture is implied by the 5-dimensional finite field restriction conjecture for the hyperbolic paraboloid.
Right. What with the quantitative estimates here? So, like, if you know what the restriction constant is, what would be the constant that you get in Kakeya?
Right. So you get 3. So if you prove the full conjecture in 5 dimensions, you get full-dimensional Kakeya. It's 3-dimensional.
Yeah, but full-dimensional, but suppose I care also about the constant.
Right.
It's not only about the b to the b, but also about the 1 over 2 to the b or something.
I can't tell you offhand.
All right. But there would be something.
So yeah, if you prove something, you can translate any result in one setting to any result in the other setting. The issue is when you're not near the endpoint, it's very, very lossy. And so I believe if you plug in Stein-Tomas and you say, what does that give you for Kakeya? It's like 1 dimension. Like, once you have a line, you already have one. It's not very good. And so if you plug in anything we know in terms of restriction, we don't get anything useful out in terms of Kakeya. But this does tell us that it really seems like we're going to need to use Dvir's stuff to to actually resolve restriction because the problem is embedded inside of it. Yes. And so that's the end.